Hi all, this is Mr. Yeager with Physical Science, looking at chemical bonding, kind of the intro to the chemical bonding unit, and having a good time here already trying to get things set up. Today what we're looking at is basically an introduction to chemical bonding. Why does it happen, okay, is really what we're looking at. And then how does it happen? Why is it occurring? And then how do we describe how that is occurring? So we are going to be looking at things called the octet rule. We're going to be looking at valence electrons. We're going to look at Lewisdot diagrams. And then we're going to begin to talk about ionic bonding some. So it's going to be quite a bit in this case. So here we go. So chemical bonding itself is when two atoms come together, and basically there's a force that's holding these two atoms together. They want to come together. Okay? Chemical bonding is something that's beneficial to both atoms. All right, it gets them to a lower energy. That's how all of chemistry is. Basically, everything happens in chemistry because we're finding ways to decrease the energy that the atoms are feeling. Okay, that's what they're working toward. So, by creating a chemical bond, the atoms, you can see, these lovely atoms are so happy, they are reducing their energy, and they come together. Okay? So, the thing is, why do these happen? Okay, I already said, obviously, it has to do with energy. But it's because when atoms come together, the reason they're trying to come together is they want to have something called a full outer energy level. Okay? Atoms are at their most stable when they feel like they have a full outer energy level. All right? So we talked about before in the atom unit, where the atom is made up of the nucleus with the protons and neutrons, and then the electrons are organized in energy levels, or the electron cloud above it. What we're going to be interested in is not all of the energy levels, just the very last one, the one on the outside. It's like the skin of the atom, all right? This is what's going to come into contact with other atoms. And so we're looking more at what the electrons are doing rather than the protons and neutrons. So you're not going to hear me talk about protons and neutrons much anymore. So we're trying to get a full outer energy level of electrons because it turns out there's a particular number that all atoms basically want, except for a couple. All right? So they're trying to create this full outer energy level. All right? Well, we give these electrons on the outer edge a special name, and a very, very important name. The electrons on the outer edge of the atom are called valence electrons. Valence electrons. These are the outermost electrons. So not all of the electrons are valence. All right? The only ones on the outside are valence electrons. And like I said, since these are on the outside, these are going to be the electrons that interact with another atom. They are, again, the skin. They are on the very edge. All right? And they're going to be involved in creating chemical bonds. So valence electrons create chemical bonds. So it turns out that basically all atoms, except for hydrogen and helium, okay, want to have 8 valence electrons. And so we give that a special name. We call that the octet rule. Obviously, octet meaning 8. All atoms have a desire to try to create this full outer energy level, and it turns out the outermost energy level can hold a maximum of 8 valence electrons. So basically what we're doing from here on out is we need to figure out how many valence electrons does an atom have, and then how is it going to try to get more or less to possibly go down to a lower energy level with 8 valence electrons. Okay? We should point out hydrogen and helium, they only need 2 valence electrons. They are on that very top row, only two elements in the top period. All right? It turns out they are happy with just 2. So if you look at some of these diagrams below, okay? And again, we don't get too much into this in physical science, but we have to pay attention to what's happening a little bit. All right? If I look at fluorine, I have all of my halogens here. Remember, halogens are group 17, the most reactive nonmetals. Okay? If you look at their first energy level, first energy level, first energy level, first energy level, first energy level. Oh, too far there. First energy level a little bit closer. First energy level. Okay? Each dot is representing an electron. It turns out on the first energy level, we can only get 2 electrons. So that's why helium and hydrogen only need 2, because they only have 2 electrons. Hydrogen only has 1, and 2 is the most. 2 is the most. So once you have 2, they're stable. But after that, every other ring after the first energy level, we can get 8 in there. Now you might see more, but I don't want you to get confused. But basically, we can try to get 8 valence electrons in it. Okay? If we look at the outer edge, though, for all the halogens, you can count. It turns out all the halogens have 7 valence electrons. 7, 7, 7, okay, 7, etc. So basically, what do the halogens want to do and when they form a chemical bond? If they already have 7 valence electrons, they want to figure out how to just get 1 more. Okay? They're not going to lose 7, they're going to probably take 1 from another atom that's willing to give it up. Okay? So the valence electrons are the ones on the outside, all right? And again, all atoms are trying to get 8. But as you can see, we're going to see in a moment on the periodic table is actually telling us how many valence electrons each group has. It turns out group 17 has 7 valence electrons. So where do we find this trend? Okay? On the periodic table is telling us how to figure out the number of valence electrons. Basically what we're doing is on the left-hand side, essentially, the first column has 1 valence electron. We're just going to count columns. The second column has 2 valence electrons. Now we're going to skip the middle for now. We'll come back and talk about that. But based on the tall columns, if I just count going across, I can figure out how many valence electrons they have. This one over here has 3. Carbon group has 4. Nitrogen group has 5. Oxygen group has 6. Fluorine group has 7. And then group 18, okay, not helium though. Helium has 2. But everything underneath helium has 8 valence electrons. So you count based on the tall column. Starting over with hydrogen's tall column, 1, 2, and then skip all the way to the other side. 3, 4, 5, 6, 7, 8. Helium has 2. Okay? And every atom in that group has that many valence electrons. So everything in the alkaline earth metals, group 2, has 2 valence electrons. Everything in the alkali metals has 1 valence electron. All of the noble gases have 8 valence electrons. Okay, I'll write that again. There it is, and there it is. All right. So just by looking at the column, you can figure out how many valence electrons it has. This also explains, going back to the periodic table, why elements in the same group have similar properties. All of these elements in the alkali earth have only 1 valence electron. So guess what? They're all going to react the same. That's why they have the same chemical properties, or they'll be very similar chemical properties. Group 2 has very similar chemical properties. Group 3, Group 4, Group 5, Group 6, Group 7, all have very similar chemical properties. Group 8 has similar. Now I stopped on 8 because what do we call Group 8? These are the noble gases. And what did we say? They're very, very unreactive. Very unreactive. Okay? Why are noble gases so unreactive? Well, now we can understand why. They already have 8 valence electrons. Do they want any more? No. According to the octet rule, they have enough valence electrons. They're fine. They don't want to give any away. They don't want to take any, so they're not going to react. We talked about how the group 1, alkali earth metals and halogens, okay, group 17, how they're very reactive. They're so reactive because they're so close, okay? The alkali metals only have 1 valence electron. If they get rid of that one, they'll go down to the full outer energy level below. Halogens only need 1 more, so they are very reactive because they're so close. They know they can go stable so quickly if they just get 1 more. So that's why they're so reactive. But that's basically it. Okay. So one more time. Basically count the tall columns. 1 valence, 2 valence. Skip 3, 4, 5, 6, 7, and 8. Again, helium is an exception. Has 2. Okay. What about the middle elements? Well, it turns out all of the middle elements and all of these inner transition metals, the transition metals and inner transition metals, they all have 2 valence electrons. All of them. So the way I usually do this is if I'm going, we go over and I go, let's count. 1, 2, 3, 4, 5, 6, 7, 8. Helium exception 2. Okay, so one more time. 1 valence, 2 valence, 2 valence, all around here that I'm coloring in. 2 valence, 3, 4, 5, 6, 7, 8. Okay, so that's how we can identify the number of valence electrons. So if I said aluminum, aluminum, I'll do this. Aluminum, there we go, 3rd time. How many valence electrons? 3rd column. They have 3 valence electrons. What does that mean? There's 3 electrons in its outermost energy level at the very, very edge. Okay? So, to help us try to show that, we create something called Lewisdot diagrams. Okay? So, we show the valence electrons by doing these things called Lewisdot diagrams. They're very simple. All we have to do is write the chemical symbol of the element that's being given and draw dots around it. Each dot represents a valence electron. Now, there is some rules to it, okay? But we'll start with this one right here, sodium. Sodium, the symbol is Na, so I'd write Na, again, capital N, lowercase a. It's in group 1, which means it has 1 valence electron. So what I do is I just make 1 dot. Now, we do want to make it a little big. You don't want to make like a little tiny thing that a teacher can't see, all right? But you just do 1 dot. Now the rule is, does it have to be on top? No, I could have drawn it like this, on the side. I could have drawn it underneath of it. I could have drawn it to the left of it, okay? But the rule is that we draw the dots on the left, right, top, or bottom of the elements, okay? But that's it. Just write out the element name, or element symbol, chemical symbol, and how many dots represents the valence electrons. So, let's do a couple more. Neon. Neon is Ne, and it's a noble gas in group 8, okay, or 18. It's the very last column, which means it has 8 valence electrons. So what do we do here? I put 1 dot on the left, 1 dot up top, 1 dot on the left, 1 dot on the bottom. Okay, wait a minute. I need 4 more. This is only 4. So what I do is then I start pairing those up. So we always draw it. I mean, that's the kind of easiest way to do it, is to start on one side, add 1 dot at a time on all sides. We actually don't pair until we have to. So we start on one side, go around. After every side has 1 dot, keep on going. Okay? But just to the number of valence electrons. So this has 8 valence electrons. All right. Oxygen. Oxygen is O, and it's in group 16, which means it has 6 valence electrons. If you didn't notice, when we get to the teens, just look at the second number. So O, 1, 2, 3, 4, 5, 6. So you can see on that one, I had to pair up 2 sides, but the other sides, we remain 1. We'd actually be marked off if you did 1, 2, 3, 4, 5, 6, because now you have an empty side. You want to add 1 dot to all sides before you go back and add a second dot. Aluminum, we already said, has 3 valence. So it only needs 3 electrons. So 1, 2, 3. Done. Okay. Nitrogen. Nitrogen is group 15, so 5 valence. So 1, 2, 3, 4, 5. Okay? You don't always have to start on the left side. It's just you have to make sure you go around once before you decide to pair them up again. Okay? So next thing, how do atoms actually get 8 valence electrons? How do they actually get 8 valence electrons? Well, there's 3 ways. There's 3 verbs, 3 actions. Okay? They can either gain electrons. Okay? They can lose electrons. And they can share electrons. All right? We are going to talk about more the gaining and losing today because they go hand in hand. If one atom is gaining an electron, one atom must be losing an electron. Okay? But the sharing is something that we're going to get into later. They're called covalent bonds. But this side over here, when I'm gaining and losing, I'm going to create something called an ionic bond. This one is going to be called a covalent bond, where they share the electrons. Okay? But so, again, why are they doing this? It's in order for them to achieve a full outer energy level, to feel like they have 8 valence electrons. So that's what we're looking at there. They can gain, lose, or share. Okay? So, So, losing something here. Here we go. So that leads us to our first type of bonding that we're going to cover at this point. So that was the finish of the introduction. Okay? Is with the ionic bonding. Okay? This is caused by when you take or give away valence electrons. So that's why I said either you gain or lose electrons. All right? When these atoms gain or lose electrons, they become electrically charged. They become electrically charged. All right? And so with that, when they become charged, it's because they have an imbalance of protons and electrons. Remember earlier on, when we talked about protons and electrons, we used to say all atoms are neutral because the protons equals the electrons. Now, what's going to happen is we're going to gain or lose 1 or 2 electrons, or maybe 3. If I gain or lose electrons, these are no longer equal, and I either have more positive or I have more negative particles, and I become charged. So how do I know whether I become positive or negative? When I lose electrons, I become positive. Now, this is something that people make a mistake on often, because they're like, oh, I lose it, so I become negative. No. When you lose, you're losing negative electrons. You're losing these negative electrons, which means your atom has more protons. We have more protons. That's right. Protons is greater than electrons. Okay? And therefore you become positive. On the flip side, if you gain negative electrons, you become negative. You're adding more negative particles. All right? So, what do we do from there? Well, if they become positive or negative, we give them special names. A positive ion is called a cation. It looks like cation, but it's cation. All right? A negative ion is called an anion. Now, a silly way to try to remember this is sometimes I try to usually show people, I go, cat with the T being a positive ion, and then anion being a negative ion. Anion. Okay, a negative ion. So if I gain electrons, I become an anion. If I lose electrons, I become a cation. Now the thing is, the periodic table is then trying to help us out. Okay? It turns out that each group does a specific thing. Again, they're all trying to get 8. So are they trying to gain or lose electrons to get this 8? It turns out metals will form cations. And then we can basically go by group saying what their charge is going to be. Group 1 is going to be positive 1. They only have 1 valence. They can either gain 7 or lose 1. They're going to lose it, so they're going to be positive 1. Group 2, the alkali metals, they're going to become positive 2. They can either gain 6 or lose 2. It's easier for them to lose 2. Then we go to the other side. I'm going to say group 13, because that's where aluminum is. The boron group, okay? They're going to be plus 3. Again, pay attention to the second number in the teens. Okay, group 13 is positive 3. So metals like to form cations. They like to lose electrons. They don't hold on to them tightly. And we just go by group. We say plus 1, plus 2, plus 3. Okay? On the anion side, they like to gain these electrons. Okay? Because they're so close to 8 already. They form anions. Non-metals form anions. So what we do on this side is I would say, is I'm going to count backwards. We got group 17. They have 7 valence. They only need 1 more, so they're going to become negative 1. Group 16. They have 6 valence. They only need 2 more, so they're going to become -2. Group 15. They're 5 valence. They need 3 more, so they're going to be -3. Okay? So group 17, the halogens, -1, -2, -3. Basically, you count away from the noble gases. And so lastly, why don't the noble gases form any ions? Noble gases already have a full outer energy level. Okay? They already have 8 valence. They don't need any more. They don't have any more. So they don't need any more, and they don't form any ions. So noble gases form none. Okay? So, going back, one quick thing with the periodic table. Real quick, come on, where are we? Periodic table, so far away. We can look at the periodic table and do this. Group 1 is +1, group 2 is +2. We're not even going to mess with the transition metals. Group 3 is +3. Group 14 I'm going to call a switch. What you're switching is from positive to negative. Group 15 is -3, -2, -1. So I usually go over the students, +1 in column 1, +2, +3. Switch, -3, -2, -1. Again, be careful. I'm just saying switch from positive to negative, but keep the number there. And that's a way you can remember all the ions for these different elements. All right? Thank you very much.